Hello all, I'm Tegan Wilson, and I'm going to be telling you about optimal Oblivious Reconfigurable networks. This is joint work with Daniel Amir, Robert Kleinberg, Rachit Agarwal, Hakim Weatherspoon, and Vishal Shrivastav. Now, to get us started, we'll start with a very simple setup. We have a set of servers, they're in a data center, and they want to be able to send messages between each other. And specifically at any moment in time, servers will have a message or a set of messages they want to send to another server or another set of servers. So a very natural question here is, how do we connect servers so they can communicate? And furthermore, given that set of connections, how do we route messages along those connections? These are the basic questions that I hope to answer using reconfigurable networks for you. But what is a reconfigurable network? Now, it used to be that if you wanted to call a friend, you needed to have a telephone operator physically connect your telephone line to the phone line of your friend. The operator was creating a physical link or circuit between you and your friend. And now we have come full circle with this new technology called optical circuit switching. Researchers have been considering implementing it in data centers. And like the telephone operator, these optical circuit switches reconfigure or change the circuits which directly connect servers to each other. However, with optical circuit switching, we can reconfigure the network at nanosecond time speeds, which I've been told is extremely fast. So how do we make best use of this technology? If we, like the telephone operator, wait for servers to tell us who to send messages to, then we'll be wasting precious reconfiguration time. So instead, we're going to try to do this obliviously. An oblivious reconfigurable network, or ORN, is defined in the following way. We have a set of n nodes, and edges between the nodes will reconfigure or change between each time step according to a predetermined schedule that we get to decide. We'll aim to additionally route messages obliviously along those connections. Now note here that the connection schedule and routing protocol are both co-designed together, and they're both designed oblivious to traffic. And in our work, we'll be limiting to deregular directed networks, where at each time step, the set of edges forms a deregular directed network with the node set. And additionally, for this talk, I'll be limiting to just one regular directed networks. In our paper, we talk about how to extend the one regular result to deregular for any constant d. So for example, take this set of 4 nodes. We could connect it in this way at time 1, in this way at time 2, and in this way at time 3. And we could have this schedule repeat periodically from here. Now, this representation is quite nice, but it's not built well for understanding routing on the network over many time steps. So instead, we'll look at the time expanded version. This is an infinite graph where nodes are indexed by both the network node and the time slot. And we call this the virtual topology of the network. Every node has exactly 2 edges leaving it, the physical edge, which has capacity 1 and represents taking a hop in the network. These are the blue edges here, and the virtual edges, which have capacity infinity and represent waiting at that node for a time step. Those are the red edges here. And this is in fact a representation of the same schedule I showed you previously. So in this network, if we wanted to route from A to C starting at time step 1, we could use this path, which first takes the virtual edge from A1 to A2, and then takes the physical edge from A2 to C3. Now this path has latency 2, since it takes 2 time steps to arrive at network node C. And one of the performance measures we'll care about will be latency. The other one is throughput, which I'll define for you on the next slide here. For our paper, we define throughput in the following way. Let D sub t be the matrix of traffic demands that originate at time step t. We say a matrix requests throughput R if the row and column sums of the matrix are bounded above by R, and R is the smallest number for which this holds. So row and column sums bounded above by R. And additionally, we say that an ORN design guarantees throughput R if it can route all matrices requesting throughput R without overloading any edges. To give some intuition behind why we define throughput in this way, note that this is a very simple local condition that each of the servers can check individually. So if we built a system that we knew could guarantee throughput R, it would be very easy to ensure that we don't overload the network without the need for any centralized checker by just rate limiting each server individually. So that motivates this definition of throughput. Now that we understand throughput and latency, we can talk about the main result of our paper. It's the following. Given a particular throughput value R, we aim to define an ORN design that both guarantees throughput R and minimizes the maximum latency L. Now, something to note here is that these two objectives are in conflict with one another. For example, if we wanted to maximize throughput, we would want to send messages along paths that use very few physical hops in the network, so we can use most of our edge capacity to originate new flow. But if we wanted to minimize our maximum latency L, we could get our maximum latency L all the way down to log n. However, that would mean most messages would need to be sent on paths which use log n physical hops. So these two are very in conflict with one another. However, this question we fully resolve up to a constant factor. This is what the trade-off curve looks like. The x-axis here is throughput, the y-axis is log scale latency. And as you can see, the curve has a very strange shape to it. It's got this curved stair step, this scalloped shape. And like this, it's a little bit hard to see where the drops or joints are coming at. But if we invert the x-axis to 1 over throughput, we can see more clearly that these drop-offs are happening at regular intervals, specifically when 1 over throughput is an even integer. Now, to describe the shape of this curve more formally, it's helpful to partition the x-axis in the following way, where we have an h and an epsilon value, and that pair is distinct for every throughput value r. H you can think of as denoting which step we're on in our curved stair steps, and epsilon you can think of as how far along the step are we. Now that we understand h and epsilon, I can formally state this main theorem for you. If we let r be between 0 and 1/2, and let L star be this function dependent on h and epsilon, then for infinitely many n, there exists an ORN design on n nodes that guarantees throughput R and whose maximum latency is big O of L star. That's our upper bound. Additionally, for every ORN design on n nodes that guarantees throughput R, the maximum latency is at least big omega of L star. That's our lower bound. In our talk, I'm going to first be going through the upper bound, and then I'll tackle the lower bound. So again, this is what the upper bound curve looks like. We handle this by splitting into two different cases. The case where we have a relatively flat curve, that's the yellow sections here, and the steep drop-offs, that's the green sections here. And we develop two different ORN designs for each of these two cases. Now, if you'll recall, these correspond exactly to when epsilon is larger or smaller, since epsilon was a measure of how far along that stair we were. And an additional tool we'll need to describe these designs is Valiant load balancing, a common trick in oblivious routing that was given by Valiant. We use this technique in both of our ORN designs, and the idea is the following. Develop first a routing protocol capital R that works for D uniform, or the uniform demand matrix. Then, to route obliviously from node A to node B, choose some random intermediate node C, and use capital R to route from A to C, and then from C to B. And we call each of those two parts of the oblivious path semi-paths of the oblivious routing scheme. Now I can define the first case for you here. Epsilon is big. This design we call the elementary basis scheme, and we define it more formally in our paper. But for the sake of simplicity here, right now assume n is a perfect square. Then we can represent the set of nodes as pairs, like so. We'll split our period into two different phases, one for each index of this pair. And in each phase, we connect to nodes that match in the indices coordinate. So for example, with this set of nodes, this is the set of phase 1 connections we'd end up seeing. And then this is the set of phase 2 connections we'll end up seeing. And now to take a semi-path from one node to another, you take the sort of obvious set of connections, the ones which take a path of decreasing Hamming distance towards your destination. And then we apply Valiant load balancing to these semi-paths to get an oblivious routing scheme. So for example, if we wanted to route obliviously from 0, 0 to 1, 2 in this example here, first we pick some intermediate node, say 2, 1, and then we route on the semi-path of decreasing Hamming distance from 0, 0 to 2, 1. It'll use this set of physical hops. And then we route on the semi-path from 2, 1 to 1, 2, which uses this set of physical hops. And this idea generalizes into higher levels H using an H-dimensional hypercube topology, where H is just the floor of 1 over 2R. It's that parameter that we saw earlier that indicated which step of the curved stair-step function we were on. And in total, for any value h, this gives an overall maximum latency of 2h times n to the power 1 over h, where 2, that factor is just coming from the Valiant load balancing. And when epsilon is large enough, this latency is at most big O of L star. Our second case is when epsilon is very small. And in this case, we're at a point on our trade-off curve where sending all of our flow on h-hop semipaths, like we were doing with the elementary basis scheme, it just requires a maximum latency that is too high. However, we're not quite at a point, our throughput is a little bit too high to send all of our flow on h+1 hop semipaths either. So this design uses a mixed approach. It sends some flow on h-hop and some flow on h+1 hop semipaths. To obtain this design, we treat nodes as vectors in an h+1 dimensional vector space over fq. So the total node space would be of size q to the power h+1. And to define phase connections, instead of using the elementary basis to get some h+1 dimensional grid topology like we were doing with elementary basis scheme, we'll use Vandermonde vectors instead and use a series of Vandermonde bases. This enables us to connect a larger fraction of node pairs using h-hop semipaths than would otherwise be possible using the elementary basis, at least when our maximum latency gets higher. And in our paper, we carefully show that this approach covers the case when epsilon is small, that we are in fact able to send enough flow on h-hop semipaths when our latency is about the right size that we want it to be. And that wraps up our upper bound section with those two different protocols. So now I'll be moving on to the lower bound section. First, I'm just going to give an overview of the techniques that our lower bound uses. We start by writing an exponential size linear program. This linear program, given a particular reconfigurable network topology, it attempts to find an oblivious routing scheme that maximizes throughput subject to a maximum latency constraint, capital L. Then we perform a trick to turn this exponential size LP into a poly size LP. And from there, we take the dual and we try to find a feasible dual solution and analyze its objective value. Now, that feasible dual solution, much like our exponential linear program that we started with, it still depends on the particular reconfigurable network topology that we started with. So from there, we bound that objective value of the feasible dual solution by a function that's strictly just in terms of the number of nodes n, the maximum latency constraint L, and throughput R. And that function will be the thing that in total upper bounds throughput. From there, we use some algebra and combinatorics to modify this upper bound on throughput into a lower bound on maximum latency. And for the purposes of time, I'll be starting us just at this dual program and just covering this last step here between these two. So finding a feasible dual solution and bounding it above by some function. So this is the dual program that we end up at. And I'll provide some intuition behind the different sets of constraints for you. This first set of constraints, it's saying for every edge in a path, these YABE variables, the sum of them on those edges needs to be at least XABT. So if we treat YABE as like edge weights that are dependent on A and B as the starting and ending points of the path, then XABT is like a minimum path length that we need to fulfill. The second set of constraints is just saying that the sum of all of the XABT must not be too small, which means that that first set of constraints will actually have meaning. That minimum path length, they're not just all 0. And finally, this third and fourth set of constraints, if we treat YABE for a fixed E as matrices, then ZE is bounding the row and column sums of those YABE variables. So in total, we're trying to minimize the sum of all of the ZEs, which means we're trying to minimize and also keep somewhat even these YABE variables. However, the YABE variables have this additional minimum path length constraint that they need to fulfill with the XABTs. So how do we do all of this? We start by defining a new parameter theta. I know, But theta you can think of as just the number of physical edges in a semi-path. And we'll define two functions, m plus and m minus, that depend on theta, a particular edge E, and either node A or node B. M plus sub theta of E and A is 1 if that edge E can be reached from A using a path of maximum latency L and theta physical edges or less. Additionally, M minus sub theta of EB is 1 if B is reachable from edge E using a path of maximum latency L and theta physical edges or less. And they're both 0 otherwise. So for example, suppose we have this path. It goes from A to B and theta is 5. And let's suppose this path has latency less than capital L. Then to define the M plus variables, we'll draw a radius of theta around node A, and we assign 1 to the edges within that radius and either 0 or 1 to the edges outside the radius. That'll just depend on if there's another path that reaches those edges from A using fewer physical edges or not. And similarly, to define the M minus variables, we'll draw a radius of theta around B in the backwards edge direction and assign 1 to the edges within that radius, and again, either 0 or 1 to the edges outside the radius, depending on if there are other better paths. Now that we have M plus and M minus defined, we're going to define the X and Y variables. We define them as follows. First, we define Y prime of ABE, that's just M plus sub theta of EA plus M minus sub theta of EB. Additionally, we define X prime sub ABT as just the minimum path length using those Y prime variables as edge weights. And then we'll be normalizing these variables so that the sum of all of the X ABTs is close to 1, but just above 1. Let's see what this looks like on our path. The Y prime ABE is just defined by adding M plus and M minus together. So this is what we end up with for Y prime variables. And additionally, X prime is just the minimum path length using Y prime as edge weights. Now, some intuition for what this edge weighting scheme is doing. You might think that instead of trying to route on a path that uses like 2 full semi-paths, so 2 theta physical hops total, that you could do better by routing on paths that in total use fewer than 2 theta physical hops. However, this edge weighting scheme makes even those paths cost as much as a path that uses 2 theta physical edges. For example, this path, even though it uses fewer than 2 theta physical edges, it uses fewer than 10 edges, it still has cost at least 2 theta, which is 10 here. And in general, any A to B path will have length or cost either at least 2 theta or at least the number of physical edges in the path, whichever is smaller. So these paths are always costing at least 2 theta unless they're significantly shorter than 2 theta physical hops. Now that we have some intuition behind what Y prime and X prime are doing, we can come back to our feasible dual and recall this is what the dual program looked like. Now that we've defined Y prime and X prime, we need to normalize them. To normalize the Y prime and X prime variables, we will need to lower bound this sum of all of the X prime variables, which is again just the sum of all of these minimum path lengths. This will additionally, once we have those normalized versions of the X and Y variables, we'll need to upper bound the sum of all the ZE variables, which is upper bounding the sum of the maximum row column sums of the YABE variables. Now to do this, both of these are looking at sums of Y variables. And we introduce something we call the counting lemma in order to help bound these quantities, which has a very natural statement I'm going to present to you now. This is the counting lemma. It states, if you have an ORN design and some node A, T can reach M other nodes B, network nodes, and at most L time steps and using at most K physical hops per path, then M must be no more than 2 times L choose K. The reason for this is follows. The number of distinct nodes that AT can reach is at most the number of distinct paths that originate at AT that use L time steps and at most K physical hops per path. Now, if we restrict to using exactly k physical hops per path, then that means that we can define this, this distinct path as just at what time steps did we choose physical hops versus virtual hops. Since we're using exactly k physical hops in that case, this would be at most L choose k. Then to get to L choose k for at most k physical hops per path, note that if k is at most 1/3 L, then the binomial is still growing exponentially. So the sum from I equals 1 all the way up to k of L choose I is going to be no more than 2 times L choose k. This counting lemma we apply in both of those cases to lower bound the sum of the x prime ABTs and normalize it, and then to upper bound the sum of the ZE variables. And then that eventually gives us an upper bound on throughput for each integer value of theta. And this is the final curve that we see for each theta. You can see here, each theta has to be an integer because it was plugged into that L choose formula. And each theta is contributing exactly 1 step to this curved stair steps phenomenon. So to get the total curve L star, we just optimize theta at each throughput value. And in total, they end up optimized at best at about theta is the floor of 1/2R, which is exactly how we defined H, defining which step we were at previously. And in total, this does give a curve that is big omega of L star. Now, I'm just going to review our results for everyone. Recall, we found a tight upper bound, which consisted of 2 ORN designs. We found a tight lower bound, which consisted of a proof. And together, those things completely characterized this throughput versus latency trade-off curve for oblivious reconfigurable networks. Next, I'd like to share some future work ideas that I have. First is ORN designs for all n, not just infinitely many of them. You'll recall that the elementary basis scheme only worked when n was an integer power. And the Vandermonde basis scheme, in fact, only worked when n was a prime power. And both of them had to be powers of h. But what do you do when n isn't one of those numbers? I have some initial ideas, but this is a question that I'm very interested in looking at. Another question is on semi-oblivious designs where we still design the network obliviously, but routing, we might optimize it for traffic. This question becomes especially interesting when we look at practical implementations, which my collaborator Daniel Amir is working on. Now, in practice, you can't assume things like fractional flow, which we assumed to make the theory proofs significantly easier. And you can encounter things like queuing in the network because of this. Some of the protocols to handle queuing that we're considering make locally optimal decisions, meaning the routing protocol is no longer fully oblivious. So how do you still analyze that that is still doing the best it possibly can? And finally, one of my dream goals would be to learn if a universal schedule exists. If there exists some connection schedule where all or even just most of the throughput latency trade-off points can be achieved simply by changing the routing protocol on top of it. If you made it to the end of this talk, thank you so much for listening. If you have any questions, please feel free to email me at teganwilson@cs.cornell.edu. Thank you.